In this video, we're going to be proving the following statement that uses inequalities. So when we're trying to prove inequalities, we're going to want to use those four assumptions we discussed in the last lecture. So we want to prove if a is greater than 0, prove that a to the negative 1 is greater than 0. And that's just the inverse of a. And recall that we're assuming that a is a real number. So immediately looking at our four assumptions that we can use for proofs, I'm probably not going to be using rule 1 or 2, because I don't think it'd be realistic to add another value c, right? To have 3 values to prove this. So it's probably going to be 3 or 4. So that's how I'm thinking about this right now. We can actually prove this by a contradiction. So, and also if it helps a little bit more, also remember that a to the negative 1, this is just 1 over a. So you say that 1 over a is greater than 0. So that's what we want to prove. And we just use a to the negative 1 just for a convention, and it'll make more sense when we do the proof. So we can do contradiction. So we prove by contradiction. So I'm going to say, assuming that a is greater than 0, I'm going to say, let's assume that a to the negative 1 is less than or equal to 0. So, and I'll explain why. So let a be greater than 0. That's our same assumption, right? We should always assume the same thing. Let a be greater than 0, but suppose a to the negative 1 is less than or equal to 0. So why less than or equal to? Well, we need to be mutually exclusive when considering all values. If we just say, suppose a to the negative 1 is less than 0, we haven't considered the case where it's equal to as well. So since we want to prove that a to the negative 1 is greater than 0, and we're going to do a contradiction, we need to do the negation of this statement, which is basically everything not covered by this. So if we want to prove that the inverse of a is greater than 0, if we're doing contradiction, we should suppose that the inverse of a is less than or equal to 0. So if you kind of want to like think of it like, oh, did I do it right? Well, you can say, you can kind of just look at all this here, and this would cover all 3 of the cases that we discussed in the last video. So it would cover the less than case, the equal to case, and a greater than case. So that's why we choose that. So we're going to assume that a is positive still, but suppose that the inverse is actually going to give us a value less than or equal to 0. Well, since a is greater than 0, so since a is a positive number, we know the inverse of a cannot be 0, right? So we can actually just say, so we'll suppose, right, we'll suppose now that a inverse is less than 0. You need to be very rigorous when doing these proofs. So let's reiterate. We're going to prove this by contradiction. So we're letting a be positive again, and supposing that the inverse of a is less than or equal to 0. Since we know that a is a non-zero positive number, its inverse cannot be 0, right? Because 1 over a inverse is 1 over a, which cannot be 0, right? That's just basic arithmetic, right? Remember in the lecture 1.3, we discussed that we cannot write divide by 0, right? So there's no way to have this value even be 0. So we're only going to consider the case where the inverse is less than 0. So which one of these rules should we use? So I kind of already spoiled it, that 1 and 2 probably won't be the most useful here. Because if you think about it, right, I mean, what values would we like add to both sides, and what values would we compare, right? I feel like this just wouldn't make any sense. So we're probably going to use something like 3 or 4. In this case, we can just use rule 3. Let's multiply both sides of the original assumption, since we're doing that contradiction, we're going to multiply both sides by a. If we do that, we get, so we're going to kind of bring this down, right? So we're going to bring this down. So if a to negative 1 is less than 0, we'll multiply both sides by a. And nicely for us, doesn't matter which order we multiply both sides. And we can say a times a inverse, right? Again, a inverse is 1 over a. That helps you. So we can write it as a times 1 over a, if you'd like, is less than 0 times a. And on the left side, I'll kind of scooch it down. The left side will get 1 is less than, right? Because a is a positive number, so the sign's not going to change. 0 times a is 0. So we use rule 3, right? If a is bigger than b and c is bigger than 0, then ac is greater than bc. Now that does sound confusing because we're using a in kind of like a different form here, right? In this case, a is bigger than b, a is bigger than 0. So b is like 0 in this case. So, and c is greater than 0, right? And c, in this case, we're choosing a, right? So that's a little weird to think of. But we're multiplying both sides by this value. And what we should do is maybe just be explicit. We can say rule 3. And what we get is 1 is less than 0. And this is a contradiction. So this is a contradiction. Right? Because obviously 1 is not less than 0. Therefore, or thus, the assumption we made up here, a inverse is less than or equal to 0, is false. Hence, you can say with confidence that a inverse must be strictly positive. And that is the proof. So let's reiterate. We wanted to prove that if a is a positive number, its inverse is also positive. And again, if you're a little confused about what this notation is, it's really just the reciprocal, since we're working with real numbers. And here I decided to prove by contradiction. So again, we're assuming that a is positive, but supposing that the inverse is going to be the complete opposite of what we were trying to originally prove. And if we can show that that's a contradiction, then it must be the other case. That's why we do it this way. So if we can prove that this is a contradiction, then it must be the other case. So since a is positive, we know that the inverse cannot be 0, right? Because we discussed this here. It's just 1 over a, and there's no value a that makes this 0. So we're only going to be looking at the case where the inverse of a is less than 0. And we're going to be using rule 3. We can multiply both sides of this inequality by a. A times a inverse is just 1, and 0 times a is 0, which is a contradiction, right? 1 is not less than 0. So therefore, our assumption that a inverse is less than or equal to 0 is false, which means it must be the other case. And that's the end of the proof.